Okay, we'll welcome Mark Jenkinson next.
Hi, thank you very much for inviting me to talk here, and I'm going to talk about FSL, and I'm one of the principal developers of FSL, and I will talk about all sorts of different ways in which you can do processing within FSL. And I'm actually going to start with something which I'm sure will make Ray cringe, which is talking about the standard pre-processing that we have, in terms of at least the standard recommendations that we would have, all the defaults which are set up within the software. But then I will talk a bit later on about the array of alternatives which we have available as well. So let's start by talking about the task fMRI. So I'll talk separately about task and resting state. So this is what the FSL GUI looks like. This is how you would set up an analysis, and this is the part of which where you specify the pre-steps. I'm not expecting you to read that. These are actually the various steps that we go through in the order that we go through them. And so you've heard lots about these various different steps in the talks previously this morning, so I'm not going to go into the details of how they work. They're within the realms of all the things that you've been hearing about. But I will give you sort of a little bit of detail and sort of, what is the nature of the different ones. So for instance, our motion correction is a 6 degrees of freedom based one. It's whole volume, so it's not slice based. We'd like to have slice based. I think that is something for the future. But at the moment it's doing shifting a whole volume, rotating all of that at once. Its cost function is based on normalized correlation, and we use a reference point which by default is the middle point in the time series. There was actually a mistake in the PDF which went out, but that's just the default. And you can choose other things. And I'll talk a little bit more about that later on. Distortion correction, I think, is a really important thing, and that was raised earlier in the talks before. And the fact that there is distortion very locally due to the susceptibility changes in the sinuses, and that to deal correctly with that, we need to acquire field maps. So you need extra data here. It's not just a sort of tick box that you do when you're doing the analysis. This is something that you have to acquire some extra data with so that you can actually do a good correction. The technique that we use to do the correction requires a field map, and that field map is either a separate sequence which you've measured. It might be a couple of different echo times worth of gradient echo data which you process, or increasingly we are getting it for free as part of our diffusion acquisitions. So the recommendation we have for diffusion acquisitions these days is to have reversed phasing co-directions. And from that, you can calculate a field map. And so there are, if you're getting diffusion data as well, then you might be able to not have to have a separate acquisition for field maps, but get it for free. We use a registration technique, or BPR, developed by Doug Grieve and Bruce Fischel, which does a really good job of correcting for it. And it's important not only in the areas which are particularly distorted, the inferior frontal and temporal areas, but it has a global effect throughout the entire brain. So if you don't correct for the distortions, there are quite often average changes that are sort of offsets, which you would see in the rotations and the translations which are applied. So we find that it has a significant effect over the entire brain, and we'd really strongly encourage people to get that. It makes a difference to your group level analyses. Our spatial smoothing was something that I thought would be talked a little bit more about by Ray, but he barely mentioned the fact that we use a slightly different technique, which is the Susan algorithm, which isn't just taking all voxels and doing a Gaussian smoothing of them, but it actually weights them according to how different their mean intensity is. So actually, when we are doing our smoothing, what typically the effect of this is that we de-weight the CSF. So we tend to smooth mainly between the grey and white matter. It's very similar to a Gaussian within those tissues, but we are not taking in contributions from the CSF when we're doing that. And we recommend a fairly small full-width half maximum for our smoothing, so that you don't pay much of a penalty in terms of spatial localization, but you do get a little bit of signal-to-noise benefit. In terms of temporal filtering, we recommend a high pass only, and that's what's available easily in the GUI where you're setting it up. We have a automatic technique that you can calculate what a good cutoff would be based on your design matrix when you're doing task fMRI, and so that's what we would generally recommend people do. And one thing that's been mentioned before is slice timing correction, and how you deal with the fact that when you're acquiring data, you're acquiring a slice at a time, and you're not getting equivalent timings in the different slices. And unlike some of the techniques that you've seen before, which is mainly based on working with the data, we actually do ours within the GLM. So this is, in a way, not pre-processing anymore. It's something that we're doing within the GLM, but it's still part of this set of things which people look at when they talk about pre-processing, in order to get rid of these kind of structured artifacts, things that we know are not ideal in the data. And so I just have a brief aside as to how we do that within the GLM. So we have different data acquired at different times in the different slices, and that's the problem. One of the solutions is to shift the data and interpolate that, and that's slice timing correction, which has been talked about before. Another alternative is to, instead of shifting the data so that it's all equivalently timed, you shift the model for each of the different locations so that now the model just matches that data. It knows about that timing change. And one of the ways that you can implement shifting the model is actually to use a temporal derivative within your GLM. So the mathematical amongst you will recognise that this is a Taylor expansion, but basically what it means is that if you add or subtract different amounts of the temporal derivative, it has the equivalent effect of shifting your model backwards and forwards in time. And so we can actually put this into the GLM and have the GLM estimate what is an appropriate shift to do, which means that we haven't actually needed to tell it about the slice timing acquisition, which is kind of a minimal benefit. But I think the big benefit that we see is that it also compensates for variations in the HRF delay. Because when we set up our model, we assume a canonical HRF, which has a fixed delay, it might be 6 seconds to peak. But we know that that varies across subjects, across regions of the brain, across levels of caffeination, across lots of different things. Not hugely, but enough that it's at the same kind of order as the slice timing effects that we're trying to correct. So we see that this is a nice way that we can correct for both at the same time. And so this is our default recommendation. And then at the end of the process, we actually do a registration to standard space and we resample after we've done all of our first level analysis. So all of our first level analysis is done in the native space of the functional acquisitions. This maps on quite straightforwardly. In our GUI, if you're sort of looking at that and if you've used it before, you'll see where all of these different things enter. I'm not going to try and get into the details of how you would set it up. Instead, I'll move on to talk about resting state. And resting state is very similar. That GUI is incredibly similar to the one that we have. For the task-based one, the pre-processing really does follow very much the same sort of steps. And these are the set of steps. So ones are very similar. The ones were pretty much identical: motion correction, distortion correction. There are some changes. Temporal filtering. Before in task-based fMRI, we had a method of calculating from a design matrix. Don't have a design matrix now. So instead, we have a recommendation of sort of somewhere between sort of 100 to 200 seconds as a period for the cutoff. And we just do high pass only. And we do that still in resting state because we feel that there's still useful information which is contained in the higher frequencies, and we're still trying to leverage that. And so that's our standard recommendation. Spatial smoothing, again, a minimal amount, probably even more minimal than in task fMRI. And for certain types of high-quality data sets like the HCP data, Human Connectome Project, we're doing none at all. ICA cleanup is something I'll talk a little bit more about later, and this is a really powerful method of trying to separate out all sort of different sources of noise and artifacts from the data. And it includes all sorts of things like physiological noise and spikes and motion artifacts. And we definitely do that in resting state, and it's an option in the task-based as well. Then there's a resampling to standard space before we start doing group analyses. So the ICA cleanup is done again in native space, and then at this point we've been moving to standard space, quite often with a reduced resolution, so that we would have larger voxels. So we might want to work with 4mm voxels or 3mm voxels. That's not a theoretical decision. That's really pragmatic based on the size of the data sets, how long it takes to process data. Again, that can be changed. And you'll notice that I haven't talked about slice timing correction, which we did in the GLM before, but we're not doing that here. And we just basically stick our head in the sand on that generally and say that because the low frequency signals are the ones which tend to drive the resting state corrections, there's not a lot of benefit in doing it. And it's certainly in our hands, we haven't seen a lot. So we tend not to do it, but it is there if you want to do it. Something which was mentioned before, which I'd really like to emphasize, is that you should look at your data. And that's not just once it's coming off the scanner, but look at what's happening to it as you're going through these processing pipelines. And FSL gives you several different ways of looking at data. One of the most obvious ones is it produces web page reports of what's happened. And a very obvious one within the prestats here is a report on the motion correction. And the most useful thing that you get from that is actually the summary measure, so it's like the frame-wise displacement measure, where you can see both a relative and an absolute version. So the absolute version is comparing it to the reference point, which is in the middle of our scan by default. So you'd see that in the middle of this, you actually don't have any, you go down to 0, and then it sort of drifts up on either side. The relative one is between one time point and the immediately next time point, and that highlights faster changes, sharper changes, which tend to be the ones which cause the problems in terms of motion artifacts. And so this is a good thing to look at, to see what's happened into your data, to get a feeling for what's going on. We also produce web page outputs which summarize the distortion correction, all aspects of sort of looking at what did your field map look like, how much did it move things, different kind of statistics based on that, and visualization of actually what did the distortion correction do? Did it actually improve the alignment of different areas? So here above you have without doing any distortion correction, and at the bottom you have with distortion correction. And even as high and as middle of the brain as the front of ventricles, we see quite noticeable shifts in the locations. And that's what I was talking about before. We really think that distortion correction gives you a lot of benefit in terms of your final analyses, not only in the distorted areas. Another tool that we have for looking, another way that we have of looking at data is to use the tool FSL View, which is a viewing tool, a very flexible viewing tool that we have. It's not how you do your analysis. You set your analysis up in FSL completely independent of the viewing tool. We would really strongly encourage people to use the viewing tool to look at what's happened, not just rely on the web page reports. So you can load up all sorts of data into FSL View, 3D, 4D data. One of the useful things that it has, particularly for looking at motion, is a movie mode, and you can actually click on that and see what's happening. Hopefully you don't see this. This is a huge amount of motion, but it will give you a feeling for not only how much motion was there in the original data when you're having a look at it, but how good a job did the motion correction do of trying to correct for that? And is there obvious motion left over or obvious changes? So that's a good thing to have a look at. You can also click around and look at time series. I have to say that I haven't used that a lot to sort of check what's going on. You can sort of see how much drift there is in your data, something like that. But quite often, time series is a pretty straightforward process. And the key thing is actually what it's doing to your design. So actually, when you're setting up the design, you actually get to see the effect of the filter. And here on the left is an inappropriate filter where it's actually changing that regressor quite considerably in a bad way. So we're throwing away some of the information, some of the power that we wanted to actually use, that we want to see, as opposed to a more appropriately set filter on the right. So that's something that you would actually see as a visualization when you're setting up the design rather than looking at what's happened to the data afterwards. But you can do all of these sorts of things and get used to trying to look at your data, because I think it's very valuable and very important to be able to do that. So now I want to spend a few minutes talking about the alternatives to what is the standard kind of pipeline and the standard default recommendations that we have. And the reason that I want to talk about that is that although we have defaults, we have to have defaults, and there is a kind of a standard recommendation, it's really not always the best thing to do. And that's because MRI is such a flexible tool. There are so many different ways that you can acquire data, so many different kinds of experimental designs. You might have multiband, you might not. You might be on a 7T scanner, you might be on a 1.5T scanner. There are so many different types of data that we analyze that there is no one shoe fits all kind of thing. It is going to be the case that, our defaults represent what is the general, most common kind of data which is coming in. And it's, relatively good at a range of data, but your specific type of data, particularly if it's a little bit different from what is the average data, is quite often going to work better with different options. And so you sort of need to think about different options and explore them when you're actually considering analysing data sets for the first time. And so there are other alternatives besides what I've discussed in the standard setup, so things such as slice timing correction. So I said that we normally do it within the GLM, but there are certain situations where that's not such a good idea. If you've got very complex designs, you can actually end up with unintentional correlations between temporal derivatives of one condition and a completely different condition. And then that can cause all sorts of problems. You don't get them between the temporal derivative of one condition and its own regressor, but you can get them between other things. And in that case, you're much better off going with the slice timing correction approach. Low pass filtering is an option. It's not an easy option in terms that it's not a button that you just click, but you can easily go away and there's a command line tool that you can run that, and then you can feed your information, your data back in to your analysis. We often need for the motion correction and the registration and distortion correction to use external reference images. So particularly for multiband, we're seeing a lot of the cases where there's very, very little anatomical contrast in the intensities within that image. And that makes things like motion correction that much harder. And we can actually often benefit from using something like the pre-saturation scans, which would often be thrown away. If we keep those, we can use those, and they're actually better for using as references for things like motion correction. And so those are other options. You can use other images. And we do within the Human Connectome pipeline, we do exactly that precisely because of those reasons with multiband data. And then there are some other ones which I want to talk a little bit more about. So the bottom four, one of them is physiological noise correction. So this is what Rasmus has been talking about in the last talk. We have a couple of different options for dealing with that. One is if you've got recordings, we have a tool called P&M, physiological noise modeling, and that allows you to take those recordings and it will do a retro I-core style correction. So it will actually detect the peaks of all of the different things within your data, and then it will model that using these kind of Fourier models, and it also allows you to have RVT or heart rate or a CSF-derived regressor. It also does interactions between respiratory and cardiac, and we've found that that can be particularly useful if you're looking at brainstem imaging or if you're looking at spinal cord imaging. Spinal cord imaging is hugely challenging, and these kind of corrections are absolutely essential when looking at spinal cord imaging. But often in brainstem imaging, they also buy you a lot to do a good job of these kind of getting rid of the physiological noise. What we actually do in terms of where it fits in the pipeline is that we don't do it early on. We actually have this as a separate thing that you would go into the P&M, you would analyze the traces, it would generate then a whole set of regressors which would go into the GLM. And these regressors are actually what we say are voxel-wise confounds, but the important thing is that they vary by slice, because the slice timing is different and the cardiac rate is much higher than lots of other things. We need to sample it differently in different slices and make sure we're trying to take things into account, particularly when you've got interactions going on and all sorts of other things. So we actually do a slice-based model when we're actually correcting for these things so that we are taking into account that information. Other things that you can add into the model to get rid of things, so was talked about before in one of the talks, was adding motion parameters in. So once you've measured the rotations and the translations which are going on in your data, you can put that information back into your model, and you can have either just those, which would be 6 regressors or EVs, or you could have a combination of those plus shifted versions plus squared versions, totaling up to about 24. And they can go in, and that can often be very helpful for cleaning up things which are motion artifacts. So Ray also will cringe at the sort of term motion correction. It's very easy to make Ray cringe, apparently. And we do have a separation between sort of motion correction, which is realignment, and motion artifact correction, where you're dealing with all of the other things which have been induced and locked into your data. You can move them around as much as you want, but they're locked in to the actual intensities. So we want to correct for those as well. And these are a couple of the techniques that you can use to do that. You can put these regressors in, and that's fine as long as you're not doing a task-based study where you've got very strong correlation. And if you've got that, then it's a problem. And that will remove most of the interesting information from your data too. So that's why it's an option to be explored and is suitable in certain situations and not in others. Another one is looking at outliers, so picking out outlier time points within the scan and actually dealing with those in a way which is very friendly to the statistics and make sure that everything is fine, both with things like temporal filtering and other processes which work like autocorrelation modeling. And not upset. Deleting data points is a massive problem for these kind of things, whereas instead we model them and we remove them in a statistical way so that all the impact that that time point would have had is removed when you're doing the statistics, but you don't actually have any problems with filtering or autocorrelation estimation and things like that. And so we have a tool called FSL Motion Outliers. It was mentioned in the first talk of today. And that estimates points within the time series where there are large changes in intensity between an image and the image following it in order to actually say that, okay, some corruption's happening here, this is an unusual amount of change, and we're going to model that out. And that not only deals with motion, but it actually also deals with other kinds of spiking which can go on. The other big thing that we have as an option is ICA-based cleanup. And this is a really powerful way of trying to separate out artifacts and that from your data. Because unlike most of the other techniques which we talked about, which either look at just time or just spatial aspects of the data, this looks at both, and it considers them jointly, and it considers them in the context of all the other things which are there. So ICA decomposition utilizes much more information about what's in the data set, and hence can separate out things which other techniques just can't when there's correlation going on. ICA is able to separate out certain sources of artifacts, so motion artifacts versus what might be interesting activations or fluctuations, which are neuronal. And there are three main ways of doing this. So they all are based on doing an ICA decomposition, so getting different independent components within a data set, and then classifying ones as being noisy or artifact that you're going to remove, and others as being the ones that you're going to keep on and analyze later. And the three ways are by hand, so that you do your decomposition and you go through and look at all of the different ones and decide which ones should be kept, which ones should go. Or there are the two ones which Rasmus introduced at the end of his talk, which is the technique called FIX, which is an automatic classification method which requires very good training data. So we've trained it very carefully on certain types of sequences like the HCP data, and that can be just run straight out of the box. You don't have to train it. But if you're working on different kinds of data, you probably do have to go down and sit and do a careful hand classification in order to train this method. Or there's Aroma, which doesn't require any training data, but is a little bit more conservative. So it's more likely to leave some of the noise and artifacts left in the data. And for those of you who are sort of not familiar with what I'm talking about, sort of ICAs and different things, you know, this is what a noise component might look like. So you can see sort of activations or not really activations, but you know, bright signals in the rim up there. That's quite classic for motion, which was sort of going in the superior-inferior direction. And you also get access to temporal information about what's going on in the time series and the spectra of the time series. And so this is what you would have to do if you were manually doing it or if you were creating a training data set. And so you'd be finding instances of components which might look like that, or instances of components which might look quite like actual real signal, neuronally induced signal, which we're interested in. And they have different characteristic patterns. They have sort of more biologically reasonable spatial patterns, as well as different characteristics in their time series. They tend to be lower frequencies. And so looking at the time series and the spectra of the time series is another way of doing it. And of course, ICA is looking at all of that together, which is, as I said, one of the ways that it can separate things out very nicely. Then I've got a single slide on some complications which have actually come up several times today, which is things like slice timing correction and motion correction shouldn't really be separate corrections. They're intertwined. They're inextricably trying to do the same kind of things, that they are affected in different ways. If you're moving your head and you're acquiring slices at different times, then it's not a simple separable process. And ideally, we'd like to have something which took into that into account, as well as things such as spatial smoothing, which is smoothing things between different slices, or HRF delays, which are actually changing the timing of the signals that we're getting. And so ideally we'd like a tool which kind of took all of that in together at once. Doesn't exist at the moment. So at the moment we're stuck doing the sort of suboptimal thing of having to have separate corrections. And there is, as I said, there's a whole range of kind of data out there. There's no single best answer in a lot of these cases, and this is one of them. Different data sets will have different levels of sort of degree of goodness of doing one order versus another order. And it's going to depend on the nature of the data itself, the nature of the motion which was going on, and the kind of analysis that you're going to run on it later on. So you'll see conflicting opinions. I don't think that there is such a thing as a fixed answer to this question. And ideally, you're in a position where it won't really matter. So good data will actually give you a reasonable result either way. If you're on the cusp, and it really does depend on which order things are going on, that's getting into the non-trustworthy area. So then finally, very, very quickly, and in no real detail at all, I'm going to talk about how the HCP pipeline, so the Human Connectome project, has lots of data, and it has an automated pre-processing set of pipelines associated with that, which use a lot of FSL utilities. So I'm not going to say anything about that except that the Human Connectome data is on young, healthy adults, typically. So that's one of the things, but it's very, very high quality data. And all of these poor individuals are scanned for 4 hours each. There are 5 main stages which are relevant for fMRI in the pipeline, and the crucial thing to know about that is that there's a surface-based stream to that. And so there's a lot of free surfer which goes on in addition to FSL. So it's really a mixture of free surfer and FSL within the HCP pipelines predominantly. But there are results produced in both ways. So there are volumetric pre-processed results and there are surface-based pre-processed results available. So it's not that it's stuck with one particular type of doing it. What we've been talking mainly about in the whole session today are things which would fit into the kind of pre-free surfer aspects of pre-processing. And one of the things which hasn't come up so far today, because generally on a lot of scanners you don't have to worry about it, is gradient nonlinearity distortions, and the scanners quite often correct for that quite reasonably. We discovered in the HCP that that scanner particularly compromised on gradient nonlinearity versus other aspects of the design of the hardware, so it actually has a much stronger gradient nonlinearity than most scans. And we had to do extra effort to make sure that that was correctly taken into account across all the different modalities. And so there is some steps there which would be somewhat unfamiliar based on everything else that we've been talking about. A collection of things which go on before fMRI, largely, I'm not going to go through this in any detail. There's this gradient nonlinearity correction. Everything is relatively familiar. And there's a lot of effort to combine warps together or to combine spatial transforms together to avoid as much interpolation, certainly repeated interpolation, as possible. And then there's the creation of these surfaces, which are going to be used later on in the surface-based pipeline. And so the volumetric pipeline is quite familiar now, hopefully. The surface-based pipeline involves some extra steps, such as how you would resample fMRI data onto the surface and being careful that you're not relying too much on the surface. You're dealing with partial volume things voxels which might sit at the edge of those surfaces, and so trying to exclude data and make it sort of as nice as possible. And so that's all I wanted to talk about today. I just want to finish by acknowledging all the various people from all different institutes who've gone into doing things which are directly related to this talk, and a whole lot of other people who've been involved behind the scenes with respect to FSL and HCP. Thank you very much.
Some quick questions.
I have a question about spatial smoothing. I thought I heard you say that for resting state data you recommend a smaller kernel than for task fMRI. So please, what guidelines should we use for resting state, and why should we use a smaller kernel?
Right, so I mean, our guidelines for task-based fMRI are a fairly small amount of smoothing. So we would typically recommend something like a voxel and a half or something like that as the full width half maximum. So the main thing is that on average we are increasingly recommending no smoothing in the resting state data, but it really depends on the quality of the data as to whether smoothing buys you anything in that. But it's quite common that we are not doing really any smoothing.
Then my question is, if you're going to do group comparison, don't you need some spatial smoothing to help smooth over the difficulties in aligning the brains perfectly?
Smoothing is often invoked as a way of sort of mopping up registration uncertainties, but it's not a fix for it, really. And so even with smoothing, and certainly the kind of levels of smoothing that we often do, if the registration is not good, you're still going to have problems. It really is a question of how well you think your subjects are registering and whether you think there is enough benefit from doing that. But it is the kind of thing that I think there is really no general recommendation which is going to fit absolutely every case. We feel that registration often works, well enough that we're not too fussed about it. But I'm sure there'll be different opinions out there, and it will vary on different data sets.
Thank you.
Can I follow up on that question? There are lots of hidden smoothing steps that we do for fMRI data. For example, if you do realignment, you may not notice, but the interpolation that you lose for that registration for transforming everything, aligning everything is going to introduce some smoothing. Even though it's very slight, it is smoothing. So you're actually smoothing a lot throughout, pretty much I think every step that we use that we have this 3D spatial processes, it does introduce some level of smoothing. So it's easy to say we're not smoothing data, but effectively you have to be very careful about that sentence that we do smooth a lot. We just don't smooth it with the kernel that everybody does it. That's what I think Mark is mentioning.
Yeah, and it's most important in sort of, tiny regions. If you're in sort of separate gyri, then actually any smoothing is likely to smooth you into an inappropriate region as well. So, it is definitely swings and roundabouts too. But.
So I have a quick question. You said instead of doing a slice timing correction, now the default for FSL is to put that slice shift or a slice shift and the derivative inside the design matrix. So my question is, you're doing smoothing before that. So when you're doing 3D smoothing, you're actually combining your slice data before correcting for it, while those slices are sampled at different offset. So is it possible not to smooth the data at that level and do the GLM analysis, and instead of smoothing the fMRI data, smooth the beta maps?
Well, the issue with that would be if you've done any motion correction, you've already smoothed across the slices.
That's right.
And so you can't really escape that, I think, short of having a method which would actually combine things together without having to do everything separately. And so I personally think that the only real solution to that kind of problem is to actually integrate these methods at a fundamental level.
Thanks.
All right, we'll get that done next year, I think.